Hello! So you just watched this half an hour long video about matrices, what they are and why we use them. But let's do a quick recap, okay? So this is, as you know, chapter 2, matrices, and inside chapter 2 we are on section 2.1, Introduction to Matrices as Linear Transformations and Basic Matrix Operations. So let's quickly summarize this. The first important concept you saw in the video was the concept of a linear transformation of vectors. Yeah. So remember, a transformation of vectors is something which has, so this transformation, which we use with this curly letter A or script letter A. Yeah. So this is our transformation, capital A. And into this transformation, we can input any vector V, and we will get as the output a vector which is equal to the transformation A applied to V. And we use the same notation that we use with functions. Yeah. So this means that an input x gets converted into an output f of x. So we are using a similar notation for linear transformations of vectors. Now, there is a very special type of transformation called linear transformations. And these are the transformations that linear algebra is all about. Okay, so it's very important for you to understand the concept of linearity. So what does it mean that A, this box, this machine that has an input and an output, what does it mean when it's a linear transformation? So A is a linear transformation if and only if, what is the condition? So the condition is the following. When the transformation is applied to a linear combination of vectors, alpha A plus beta B, then the result is a linear transformation of the outputs. So the result is alpha times the transformation of vector A plus beta times the transformation of vector B. And that's it. That's the definition of a linear transformation. If the transformation fulfills this property for every possible vector A and B, and for every possible scalar alpha and beta, then A is a linear transformation. As I explained in the video, linear transformations are the equivalent of multiplication, but acting on vectors instead of scalars. Yeah. Okay, so next thing you saw is that any linear transformation, or every linear transformation, can be represented as a matrix vector multiplication. Yeah, and this is how it worked. So the linear transformation of a vector V, you can always write vector V using expanding it in a certain basis. Yeah. So if we expand vector V on a certain basis, it's equal to V1 as a scalar times the first basis vector E1 plus dot 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 until Vn times the basis vector En. Yeah. This is the definition of a vector. So this would be the vector whose coordinates are V1, V2, etc. up to Vn in the basis of the Ens. Yeah. So we substitute this vector inside the transformation, and then we apply the linearity of the transformation. So the property that we just described. So we have linearity of the transformation. And this means that the output of this transformation is the coefficients that were actually the coordinates of the vector, but now they are acting on the output of the different basis vectors. Yeah, that's what this is telling us. And then what we do is that by definition, that's what this equal sign with a def on top of it means. By definition, we say that this is the same as multiplying a matrix A with the vector V. Yes? And the matrix A is formed by placing as columns, yeah? So the different columns of A, so the first column of A is equal to the transformation applied to the first unit vector of the basis we are using. The second column of A is the transformation applied to the second vector in the basis, and so on. So every column of A is the transformation applied to each of the vectors in the basis, for whatever basis we are using. Normally, and for all the problems we will do in the first 2.1 section, we will be using the basis x hat, y hat, z hat. Yes? Now I also showed you a trick for how to remember how to do the multiplication of a matrix times a vector. So this is a trick to remember. So what was this trick? Let's say you want to multiply this matrix 1, 2, 3, 4 times a vector, let's say 1, 2. So the trick was the following. Let me move this here, and now I'm going to move the vector, the 1, 2 vector, and I'm going to move it up like that. I slide it up, yeah? And this means that I leave an empty space here. And this empty space has 2 slots, right? So each of these slots I have to fill with what? Well, what I do is I get the row that points to the slot and the column that points to the slot, and I do a dot product between them, okay? Which means I do 1 times 1 plus 2 times 2. That's 1 plus 4, that is 5. And that is the result I write here. Now I do a similar thing for the second slot, yeah? So in the second slot, what we have is this row coming in and this same column coming down. So therefore I do 3 times 1 plus 4 times 2. That's 3 plus 8, which is 11. So I write 11 here. And that is the result of this matrix times this vector. So we can say that 1, 2, 3, 4 times 1, 2 equals the vector 5, 11. Yeah? So with this trick, you will always remember how to do a matrix vector multiplication. So next, I will do a video showing you examples of finding matrices associated to certain transformations by doing this trick of placing the columns as the transformed versions of each basis vector. So, see you very soon.